All right, hey everyone. We are officially live right now. And welcome to the first live stream of our C++ Denver meetup. We'll see how this goes. We have Charles speaking today about his ConstExpr RayTracer work, which is a talk that was accepted for C++ now, but unfortunately, as we are all aware, that conference got canceled. I do have a JetBrains key to give away this month, but we'll do that in the pub happy hour coming after Charles's talk. I don't think it makes any sense to do that live on YouTube. So please put comments in the live chat if you have any questions for Charles. There is definitely going to be about a 30-second lag or so between the time that you post a comment and he's able to respond to it. And Scott's also on here with me. Scott, if you want to say hi. Let's see. Anything else that we need to go over? You mean for May? I don't think we have anything. Do we have anything definite yet? We have a few things in the work, right? Okay. I'm getting a comment here that we can't hear Scott. That is unfortunate. So, no, they won't be able to hear you either. It's going to have to. I have to do something. Yeah, you do. Yeah, yeah. Hold on. I need desktop audio. This is terrible. Good thing we know what we're doing and we are all professionals here. Um, sorry, I am trying to figure this out. I don't know why it's not capturing my regular audio output. Can you all say something?
I can. I'm.
What is sorry for the delay. Okay, so I believe that you all should be able to hear Charles now. Sorry about
Oh,
that.
oh, can we get some confirmation that my voice is not completely gone or silent?
Let's see if we get any confirmation on the live chat here in just a moment.
Yeah, there's a good 10 to 20, probably 20 to 25-second delay on the video.
Okay, so I am live. I don't know about Scott. I hope he is too.
Yeah, no, so I had to
I'm not
redirect
dead,
all of my
as
system audio
my voice hopefully
output, so.
indicates.
Okay, you're good. Go for it.
Okay. Hello, I'm Charles Eason. I'm going to be talking about my ConstExpr RayTracer. The tagline is the world's fastest ray tracer, with a little annotation that it's runtime ray tracer that it's fast at. Anyways, quick. Sorry about the delay. I have figured out I can draw on the screen, which I may be using. But a quick disclaimer, my internet is not perfect, so if there's some sort of audio shenanigans, that means you can't hear me. Please let me know and I'll repeat what I said. So, oh man, 30 to 40 second delay on chat. Oh, that's going to be fun to deal with. Anyways.
Yeah, we'll queue up the questions and then we'll ask them as it goes along here.
Okay. So, as I said, I'm Charles Geeson. My current position is at Lunar G, which makes the Vulkan SDK. So if you have any questions about Vulkan graphics or anything GPU-centric, I'm the guy to ask. But enough about me. So I, in January, wrote a RayTracer that is purely using ConstExpr, which is very descriptive of itself. I called it CERT because I needed a catchy name, CERT, ConstExpr RayTracer, but there's so the thing that makes it different than other ray tracers is that it operates entirely at compile time. So when you compile the program, you're not just generating machine code, you're actually generating the output image and storing that in the binary. You aren't whenever you run the ray tracer, all it does is it prints out an image. It doesn't do any computation other than figuring out the size of the bytes to put out. So it runs in literally 10 milliseconds or less. And I have profiled it and found it to be basically 0 seconds to run, but then about 15 milliseconds for operating system related file I/O and just getting the data onto a file. And while it is the world's fastest ray tracer, like you look at Pixar, who takes 24 hours to render a single frame, my ray tracer's time does not compile time, which is not non-zero. So here's an example output from the ray tracer. If you notice, it's a bunch of spheres. Some of them are reflective, some of them are, matte finish with different colors. There's lights with shadows, and there's a background blue sky. Pretty big ray tracer. I did not shoot for the moon in terms of features. I shot for something that was mostly achievable. So I do want to do a quick demo, and can I make this bigger? I just realized how small this is.
There it goes.
Nope. Font. Oh, I think I can. 2836. Let's go. There we go. Okay. So these are the timings I was doing, but I'm in my build folder, so if I just do Ninja clean and then Ninja, I can show you it compiling, and it will take a couple of seconds to compile because it's, well, a compile time ray tracer, so it's doing all the computation while it's compiling. And as various threads are coming in and out, and so we'll finish in a second or two, and then we can run it. And unfortunately, it's not that. Oh, there we go. Finally finished. Okay, so we can insert, and then to view it, because it's just an image, I have to go to the folder where it's contained, and I will bring it up. Okay. So I have it being output to output compiletime.ppm, which is this thing. So I'll open it up. Nope. Well, this is actually the image, but since I store it in text, this is what the image really looks. What it looks like. It's actually opening it. This is what it just compiled. I made it really big so it's easy to see, but the actual size is so in about 30 seconds it was able to render this image, which is bad, but it's not that fast. Anyways, so that's enough demoing for now. Okay, so a few project specifics. It is using C++ 20. and using some of the features only available in the latest compilers. So I started with Clang 10, but now I'm using Clang 11 because it's the latest and greatest in Clang goodness. The RayTracer, if you know anything about RayTracers, this word may mean something to you, but if you don't, that's okay. I designed it around a Wittened-style RayTracer, which was named after a guy who was named Wittened, who came up with a RayTracer in the 80s. So it's not a new style, but it is what it is. And if you want to view the source code for it, you can find it online on my GitHub page. So cdgeeson/cert. I don't have an easy way to copy and paste the text into chat, but if someone else wants to do it, feel free. So onto the actual specifics about the project. I said, what?
Before you move on, Charles, we had a question here from Chris asking if you have benchmarks coming up for the compile time versus the compile time runtime solutions and what the time differences will be.
I do. They're at the end, though. So
very good. Then we will get to that.
I can skip ahead to them.
No, don't do that.
Yes.
Okay.
No, skipping's silly. Anyways, I do have benchmarks, both comparing the compile time and the runtime version, because I do run it in a runtime context to compare to how it would be if it was a normal RayTracer. The genesis of the project was it was Christmas break, and my friend had sent me a link to a compile time linear algebra library, and I thought it was pretty funny. Like, hey, my friend does machine learning, so he was developing a machine learning library of linear algebra functions, and he was doing it at compile time using templates and then later ConstExpr. And I thought that was fun. So I was like, you know what? I could do that, but doing it with a RayTracer. I like graphics, if you couldn't tell already, if you have met me before, but one of the things that I have not actually done before was write a RayTracer. I've only been doing rasterization and real-time stuff. So I took this as a real opportunity to do something I wouldn't normally do in my day-to-day projects and other activities. And because it has an interesting spin on it, I felt motivated to actually see it through rather than just do what everyone else is doing, which is what it would have been otherwise. It's really fun when you have a fun project to work on, but you made it your own in some way, and that's what ConstExpr did for me for this project. I'm not going to name the linear algebra library for mainly anonymity and to protect the innocent. I also do not have the link to it easily available, so it's kind of a cop-out of an answer to say I'm protecting the innocent. Because the last time I looked for it, it took me 20 minutes to find the stupid link. It was really annoying. Anyways, and the sad thing about this project is it quickly spiraled out of control as I realized it wasn't just a quick joke, but it actually was an interesting project in and of itself. So I used the venerable ray tracing in one weekend tutorial, blog post, article, what you call it. It is something I would highly recommend to anyone who wants to write their own ray tracer. It takes you from zero to hero, and you don't have to know any specific thing other than basic programming. And so I was able to follow along and actually build a ray tracer, and then what I did was modify it to work in ConstExpr. The link for it is on the screen. You can easily find it if you look for ray tracing in one weekend. So if you look at the source code and you've gone through ray tracing in one weekend, you will notice how similar they are, even if parts of it are very different nowadays. I've been talking about ray tracing for the last 10 minutes, and I want to be clear what that is. Not everyone in the audience will have is familiar with ray tracing, and so here's a quick visual demonstration. You have a scene full of objects, cubes, spheres, what have you. You have a camera that's your viewer into the scene, and then you cast rays into the scene that simulate light as propagates through the scene. It's a critical component to 3D animated movies, special effects, and even scientific research, where they're simulating light rays to see how it reacts in a physically accurate system. So I'll be diving more into how it works later on, but that's a quick rundown of what ray tracing is. So there's many different parts to a ray tracer. Obviously, you have math. If you're doing light rays, you're going to be doing 3D geometry processing and linear algebra, and you'll need some common math stuff like square root and sine and cosine and tangent. I was thinking of logarithms. That's the other one I was thinking of. Oftentimes you'll do pseudo-random number generation for various components. You'll have to have some vector and ray classes or components or objects, and these will have common operations like dot products and cross products and normalization. I'm not going to get into the weeds about what those are, other than square root, as you'll see later on. But they are integral parts of the ray tracing component. If you ever want to see the output, you'll need an image to put the pixels into, and for the ray tracing algorithm to work, you need to be able to put rays into a scene and figure out what they hit. So you'll have a ray starting from the camera, going into the scene, then hits a sphere. You need to be able to tell what it hits. Did it hit a sphere? Did it hit a plane? And then you need to be able to tell where it hits. And the last major component of a ray tracer is figuring out what the colors should be at the points the rays hit. So if you hit the ground, you should probably, if you have like a grassy floor, you'll want to be able to figure out, that's going to need to be green. And if you hit a metallic sphere, you need to be able to reflect the light as it bounces off the metal sphere and into the distance, and figure out what that ray colors will be based on the reflection. So because I wrote it as a ConstExpr, every component I just mentioned previously has to be ConstExpr. And I just quite literally listed 5 of the different components and mentioned how the things that I would normally reach for, like the standard library, a lot of the standard library isn't ConstExpr, even in C++20. So CMath is not. So I can't use a square root, sine, cosine, all of those family of functions. I cannot use them in a ConstExpr context. I can use stood vector if it was implemented, so I had to write my own. Random is also not ConstExpr, and that's actually a really thorny one, because every time you call a random function, the random number generator has internal state to keep track of the next number to generate. That way you can generate more than one random number. But to implement that, ConstExpr doesn't allow for static state. So like you can't have a global variable that you permute every time you call the function. So that was an interesting problem to solve. The actual ray tracing algorithms, the materials, the surface interaction, all of that needs to be ConstExpr friendly, but on the whole, that is just a math function. So it takes in a couple of properties and then figures out what the color output should be. So those are not intractably difficult. So they're just, they just need to be ConstExpr. So you can't use any constructs that are not ConstExpr. And I think the most important part that was not easily solved was getting the image from ConstExpr to runtime. So having it persist between the compiler and into the program binary. And I'll be talking more about that later. So as a quick recap, what does ConstExpr mean? If you're watching this, I assume you know what it is, but for all those who may not, and for people in the future who are watching this, ConstExpr is compile time execution of code. You have a variable and you want to initialize it to some value, but that value is not some literal you typed out with your fingers. It is an expression that you compute using a formula or a function. And it was added in C++11 and in 14 and then 17 and then C++20 have added new capabilities to it, but it is still a subset of the entire C++ language. I have a few listed things you still cannot do and may never be able to do depending. So exceptions, assembly, file I/O, all those kinds of things are not possible inside ConstExpr at all. So I want to be clear what the difference between a ConstExpr variable and a ConstExpr function is. A ConstExpr variable is a variable whose value is initialized by the compiler using some expression. A ConstExpr function is simply a function that can be run at compile time. So if you have a function and then you add the word ConstExpr to the front of it, the compiler goes, oh, I can use this function anytime a ConstExpr variable needs to be initialized. So the benefit of this dual nature purpose, dual being both you can run it at compile time and at runtime, is that you can easily debug your compile time constructs. And I do this a lot. In fact, if you go and download my RayTracer, there is a runtime version of it that is significantly faster to run, and I use that for debugging purposes and just for iterating and quickly coding up features. So a recap of the two major features that were added that I use to ConstExpr features it is, and then a few more that were neat to have. So dynamic allocation. Before C++20, a ConstExpr function could have many things, but it could never allocate memory. So you could only use stack full objects. If anyone's seen Jason and Ben's ConstExpr All the Things, you'll have seen the various escapades they went through to get around this restriction. C++20 completely opens the can of worms and lets you create memory and destroy or create pointers to memory allocations and then destroy them inside ConstExpr. And it's such a relief because it makes so many constructs more amenable to a ConstExpr computation. Like vectors and strings, which are components of many C++ programs, are now usable inside ConstExpr, whereas before they were completely banned and would never compile. One of the requirements is that you delete all the memory you allocate. If you fail to delete memory, the compilation fails and you get a compile error, and then your program does not produce a usable binary, which means it's a pretty nifty leak detector as long as you actually exercise the paths of code that allocate memory. But it also means that you can have pointers in ConstExpr. I'm not sure if you couldn't before, but I don't think they would be very useful at compile time if you can't allocate memory, because if taking pointers to stack allocated objects is never something I consider good practice, but I digress. The other major feature that I used that was added in C++20 was ConstExpr virtual functions. It enables classic object-oriented programming style constructs to be used. Dynamic dispatch, polymorphism, virtual functions, all names under the umbrella. And it lets me have an interface with a virtual function that various implementation classes can implement and then extend the behavior. And I use this in several places in my code base. I see your comment, Ben, and I actually think I typed this out without a compiler, so I don't think this compiles. Now that I noticed that is a bug. So, good eye.
I have to agree, that's probably a bug, yeah.
Yeah. It sounds like I need to edit my slides later. Anyways, so a few other features that were added that I'll try to quickly recap because they're interesting, but I don't use because I don't have a reason to. You can have unions with you can change the active member of a union, so you can have stood variant and co inside ConstExpr. Stood is constant evaluated, lets you change the behavior of the function based on whether you are running it at compile time or at runtime, which enables various other things, which are listed below. The unevaluated assembly and the try-catch blocks you can have in ConstExpr function, you just can't use. But because of stood constant evaluated, you can actually have the same code, the same function used in both ConstExpr and non-ConstExpr contexts without having to do weird build or macro shenanigans to get things to work. ConstEval and ConstInt are the two keywords that were added. The ConstEval lets you demark a function as only compile time, and ConstInt is a ConstExpr function, but no, it's a ConstExpr variable that is not const. If you want to find out more about these things, there are plenty of other resources online, and I just included them for completeness sake. So how did I code it? I started with a world. Everything. It has all the shapes, the lights, and materials that are in my scene, and it has one job, which is to perform ray traversal. It gets a ray, iterates through the shapes, and then returns what it hit. I have shapes. Shapes are used in abstract base class using that ConstExpr virtual function I alluded to earlier. I only currently implement spheres because I'm lazy, and spheres are just enough to test everything, but I also got lazy and just didn't have time to implement, triangles, cubes, and planes and other things. So that's fun. If you look closely, the image I put in the slide, the floor is actually just a giant sphere. It's a cheap trick, but the sphere, the shape interface has two functions: intersection and hit. Intersection, intersection is for light ray testing. So, like, is there anything, not light ray testing, occlusion testing, saying I have points. Is there any in between these 2 points? And then the hit is, okay, I'm going to put a ray. What is the closest thing? No. I have a ray through the scene. Does it go through the shape? And if it does it? What does it hit? The actual surface details. Here's the code that implements it. I have a hit record struct, which is just the return value for the intersect and hit functions. Actually, no, it's just for the hit function. The intersect function is a Boolean return. It has a Boolean in it saying, hey, did you hit something? And the t distance to the ray origin is used for determining the closest object that was hit. If I hit multiple things, sometimes I need to go, hey, did I hit the first thing or did I hit the second thing? And the second thing was closer than, I hit the thing. The normal is the p and normal are used for material calculation, and the material pointer is the material that is going to be used. As you can see, I just have a pointer to material. It's a raw pointer, but because it's not owning, it's very clear that you don't do anything with it other than use it. The material class, since we're talking about materials, it defines surface properties. So if you had a grass, if you had rocks, if you had, I don't know, a window, those would be encoded as materials, and they describe the properties of the surfaces that are hit. I have 3 implemented. I have a diffuse, so that's like your matte surface with a solid color. I have glass and metal. So metal will reflect, then glass will reflect and refract. So that then creates cool effects where you can see through glass and see what's behind it, but also bend through the object as it's refracted. It's also a base glass. As I find it's very simple to work with, and I'm not uber concerned about performance, so I'm fine with that level of indirection. Interface is strikingly similar to the material interface is very similar to the shape interface. It has a struct that's your output parameters or output values, and then you have your material class with a function that returns that value. And so that's how I'm getting my data out. And if you notice, I have ConstExpr slapped in front of every variable, every function in my material class. I also have the same thing for my world and my every class. So I just want to point out that ConstExpr can be very wordy at times because you have to write ConstExpr in front of everything, literally everything. Anyways, okay. So I also have lights. A more sophisticated renderer would have a more sophisticated implementation of lights, but for my purposes, I only have a point lights, I should say, and that's because they are very cheap to compute. And I found I needed as much speed as possible, and so I went with the lowest common denominator for something that looks kind of right, but is also very simple to compute and use. The more sophisticated lighting you want, generally the more computation you need, and so that's why I went for the most simple version I could, which is just a literal point that emits light in all directions. So now that we have all the various components, so we have a world full of materials, surfaces, and lights, we need to actually trace those rays, and I have a general description of the algorithm. You first get a ray that you trace through the scene, you figure out what was hit, if it hit anything at all, then you need to determine the light of that point which was hit. You need to figure out the material value that was hit. So if you hit the ground, you need to figure out, okay, what was the color of the ground at that point, and then you incorporate the lighting value you got from the sun, maybe a flashlight in the distance. And if your ray happens to hit a shiny surface, you need to then do a secondary ray starting from that point. So if you had a mirror, you'd have a flat plane, and all the rays that hit that mirror then have to bounce off of it and then go off and figure out what the heck is reflected in the mirror. And if you have a second mirror after that, you have to do a third ray and a fourth ray, and so you can quickly get an explosive growth of secondary and tertiary rays. But once you figure out all the values of those rays, you combine them together and you get a single color value for each pixel. This is the code for that, and I included it simply for completeness sake. It's pretty heavily nested. I mainly want to point out the scatter function, the world hit function, and then the trace functions. So there's multiple traces, but the point is that they are recursive in nature, so I will figure out what kind of surface I'm hitting. If I'm hitting glass or metal, I need to do a secondary bounce. If I'm not, I don't. The material scattering here is for figuring out what the color is at the point it was hit. And if nothing was hit, you use a background color. You can use like a procedural, like a sky shader if you wanted, but I just simply chose for a single color. And then when you have the ray tracing algorithm, you then need to drive it at a per pixel. So I have a double for loop that goes through all the pixels in the screen, for every row, for every column, and it will trace a ray at the X, Y coordinate, and then sets the color into a frame buffer. And then it simply returns that frame buffer. And so, in a brief nutshell, that was the entire RayTracer algorithm. Hopefully I didn't confuse anyone, but hopefully that makes it kind of clear what all is going on. I think that was a little bit fuzzy because there's a lot of details I completely glossed over, and a lot of things I quickly looked over just because I could be here all day explaining each and every individual component, but you guys weren't here to hear about what a RayTracer is. You were here to hear about the ConstExpr part of it.
Well, if you would like to, you can pause for a moment here while we see if anyone on the stream has any questions.
That'd also help me drink some water.
It would. I would like to point out that writing on the screen does seem to be working quite well given the situation we have here. So I think that was a good decision. And just an aside. Sorry, go ahead.
No, you go ahead.
I was going to say, as an aside, on my slides, I have started to make keywords like ConstExpr and no discard in a grayed out font so that it doesn't look like it's so noisy when I have ConstExpr on every single line of the slide.
There's a lot, these slides with a lot of code on them. I just kind of I tried to make it as short as possible to fit on the slide, but I'm okay with there being a lot of visual noise because it's not a simple algorithm. It's just, and it is what it is. Should be.
All right. Well, I don't see any questions coming in, and I think they should have caught up with us by now. So I feel like you can go ahead and good advice. Okay, go ahead, move for it.
Okay, so the first major hurdle I had with getting ConstExpr output was getting the image out. So I went through ray tracing in a weekend, and I got through the first couple of chapters, and the first couple of chapters are just setting up your environment, setting up vector class and some other stuff. And one of the things they also did was printing an image to the file so that you can actually see the output. ConstExpr, that proved to be a little more complicated than initially.
Sorry to interrupt again, but there was a question here that asked if there's any reason to declare a ConstExpr local variable inside a ConstExpr function.
No.
I can add something to this, I believe. You
Sure,
can't.
Please.
You simply can't. If you try to put a ConstExpr variable inside a ConstExpr function, you get a compile time error.
That actually may explain some of the weird compile errors I was getting.
Okay.
So I was looking through my code, and I think the this is confusing. This is actually this is supposed to. It looks like it's What I'm trying to say is that the ConstExpr word makes it look like it's a variable, but it's not. It's a part of the function declaration. I should have formatted this a little bit better. Anyways.
Charles, hey, this is Scott. Yeah, I might suggest that I see that you now have a title slide. When you hit your title slides, because we have about a 30-second delay, between your voice and what shows up in video. It might be good
Oh,
to, or at least there is a lag. So
Yeah.
you might skip over the title slides. Like if you hit a title slide, just go on, because by the time your audio gets caught up to the video, you'll be pretty close.
okay.
Just a suggestion.
That works for me. I can do that. I mean, I have in front of me the function that I use to output data to the screen to a file. I first have to get the data to output, which is this frame, which uses the ray trace function, and you give it a width, a height, and the samples, and then you simply iterate through the frame, and for each pixel you print out an R, G, and B value. If you saw it earlier, the ppm format is literally just a text file, so each of those RGB values are just a number from 0 to 255. So it's a very simple text form. What I found was difficult getting the data from compile time. I couldn't just create a vector and then pass it in between it, because the vector is dynamically allocated, and so you cannot leak memory from compile time to runtime. Jason has a C++ weekly that talks about this, and he actually provides a solution for it. And at the time he made the video, there was no compiler support for it. But I went back and I actually implemented that function and those functions and found it worked exactly as he described. And so in front of me, I have a quick and dirty recreation of it. I create a ConstExpr array, so a dynamic array. I mean, so this would be a stand-in for std vector if std vector was supported, and so it just returns a dynamic array. You have two helper functions. You have your main function at the bottom, which prints everything. It has to get to the data and then just simply iterates through it. There's two helper functions. The first, the get size, is getting the size of the vector. That's all it does. Thankfully, it's very well named. And then we have populate data, which gets the ConstExpr array, then creates an array, a std array of the size of the array. Then this was using, in Jason's code, he used a std algorithm, which I also worked if std vector was supported, but it wasn't, so I had to use just a basic for loop. But then you return your array, and now you have your data that was created at compile time, and it now magically lives into runtime using a std array. Okay.
I'm glad it worked.
There is, yeah, I was actually surprised. I thought it wouldn't, not gonna lie. I thought there was gonna be like one little weird thing that you forgot or something. And everything that was wrong was just because std vector wasn't implemented, or some other compiler feature didn't exist yet. Anyways, there's a problem with this code, and it's not a problem in that it doesn't work. It's a problem in that it works extra. It runs get ConstExpr array twice. So if you have some expensive computation, this method will do that computation twice. And I couldn't quickly find a way around this, and I don't know if there is one.
It didn't get memoized.
You can mitigate it by just saying, okay, it may be memoized, but I'm not going to hope the compiler does it. I would like to know that the compiler cannot accidentally run this twice. The thing I found, and this is an aside, I did not find excessive memory usage in my ConstExpr work. I only found like a couple 100 megabytes of RAM usage at most. There has been previous ConstExpr, and no, not ConstExpr, but yes, ConstExpr RayTracer. I don't have a link to it in my slides anywhere, but there is a ConstExpr RayTracer that uses all the RAM of your system. It uses like 6 or 7 gigabytes for a single thread or a single compilation unit because of that memoizing. I believe they were using GCC, and I don't know if Clang doesn't memoize ConstExpr results, but I did not find runaway RAM usage, which is good because my computer didn't crash every time I tried to run my RayTracer. So, getting back on topic, fortunately, image output, because I am saying I'm going to ray trace a 100 pixel by 100 pixel image, I know exactly how large the output image is, so I never have to deal with it. I never have to deal with this problem. A possible mitigation would be saying I might have up to X elements, and then you return a std array of X elements, but your code only uses the first N of them. So basically, some sort of you have a maximum capacity that you figure out you might need, and then you return an array of that size, but you only need so many of the first N. So that's thankfully this problem wasn't something I had to deal with, and I was just able to use a templated std array to get my data in and out of ConstExpr. Really just out.
Okay. You're at another title slide.
Yes, math functions.
So Leslie had a question here that asked if the populate data function should be consteval.
I hadn't thought about that. And I would say if you're doing something that is only going to be run at compile time, then definitely yes. All of my work has both ConstExpr and runtime evaluation as a requirement, so I don't use consteval anywhere because I need to be able to run it at runtime as well as compile time.
Okay.
So hopefully that answers your question, Leslie. There are many math functions I need to do ray tracing, but the only really interesting one is square root. All of the other ones either share very similar implementations or very similar problems in that they so square root, it's the big thing about it is that it's hardware accelerated these days, and so whenever you call square root in your math code, you're more than likely calling you're calling a CPU instruction for some silicon in your CPU or GPU, making it very, very fast. ConstExpr has limited standard library support, and the one that's the most painful for me is the lack of CMath. CMath.h is typo. I should have put CMath or math.h, but hopefully you understand that it's the C standard library functions for square root, and that it is not ConstExpr. I hope in 23 we can remedy this, but for the meantime, I have to use an iterative approach, which means manually calculating out the value. This project actually turned into a nice recap of my numerical methods class I took a couple of years ago in university. So I actually was applying several of the things I learned in that class for once, because I had no other use for it before. So a popular way to calculate square root numerically or manually, so to speak, is to use the Newton-Raphson method, and it basically is a Newton approximation. I don't know if it's approximation is the right word, but say the mathematical formula which, given a number, calculates the square root. And it was the code for this I have mainly taken from Ben's ConstExpr experiments. He has a bunch of ConstExpr math functions and their implementations, and it was written in C++11, which required a bunch of ternary operators, so I turned those into just general if statements with recursion, and then I found that I was exceeding the max stack limit, so I also turned those into iterative functions. So hopefully I didn't have any typos in the transcription from ternary operator to recursive, then recursive to iterative function. But as you can see, there is a while loop that keeps iterating a function cur gets 1/2 of cur plus x over cur, and keeps iterating that until the previous value was more or less the same, as in any further iterations will be useless because you've already arrived at the destination. It's slow. It is very slow. The reason it's slow is because I need high accuracy. If I didn't want good accuracy, I could reduce the number of iterations, but that doesn't really make me happy. And so I started looking up various methods to make this fast. And a long time ago, I heard about a game called Quake 3, which had this fast inverse square root function that magically sped up square roots, because at the time Quake 3 came out, the square root was not a function that was in Silicon or was widely available in Silicon. So you had to do it manually like I'm doing it now. Then there is issues with the floating point comparison. I have an actual function to compare floating points, but I chose to use the much clearer not equals to rather than a function that says equal, and then people are wondering, why do I have a function to compare two numbers together if they aren't already familiar with floating point comparison. Unfortunately, I don't have any slides talking about floating point comparison, but because it's not actually really specific to ConstExpr, I just kind of left it out. So I do have tests, and they're mainly just me doing calculations. They're really just me writing out the function with a bunch of different input parameters and output parameters and manually checking that, do these make sense? So I hope those answer your questions. The fast inverse square root function is a story and a half that I'll try to quickly recap, but it works by evil bit hacks and then really crazy shift, a weird shift with a subtract, just a magic constant that magically produces a square root value. And I tried to implement this because I thought it'd be cool. And if you want to know more about the fast inverse square root, its history, you can Google it. There's various articles. There's a really good research paper written about the subject that goes into detail where the magic comes from. So I implore you to look that up on your own. So, I got ahead of myself. I have a slide doing all that, and I said it before I got to the slide. Hopefully you guys can look at this and read it yourself. So I tried implementing it myself, and I couldn't. Because of undefined behavior, ConstExpr disallowed any and all undefined behavior, which this function, fast inverse square root, relies heavily on. Those bit hacks where you reinterpreting a float as an int and vice versa, no, can't do that. That's the major pain point of it. There are other ways to implement that kind of thing, and all of them are all disallowed in ConstExpr. You can't memcopy, you can't reinterpret cast, you can't type pun through a union, because all of those are UB, and anything that's UB is disallowed, so therefore I cannot do it. And I did not want to invest 20, 30 hours in trying to break the compiler, because if the compiler is doing its job, all of the methods that I know of and that people use are just not literally possible. And if they were, it would be a compiler bug, because in ConstExpr, UB is not allowed. So I kept looking because I was hoping that maybe there was something that was not UB and I could use. And there is. And it is in C++20, and its name is Bitcast. And it is literally custom built for this exact purpose. If you watch some of the CppCon talks about it, they actually use fast inverse square root as an example, because Bitcast lets you say, hey, I have an int, pretend it's a float. And hey, I have a float, pretend it's an int. And you can do all the type punning you need. So I was like, oh man, this is, I got my hands ready to start pounding away at the keyboard to implement it. So I looked it up, and Wikipedia has a very helpful default implementation. And one thing I noticed is I use this memcopy, which I went, oh, that's a little weird. But then I read the comment in the middle of the page that dashed all my hopes. And it was that ConstExpr support needs compiler magic. And so I was back to square one, because magical was going to solve all my problems had not been implemented yet. So I was hoping the default implementation on CPP reference had that magic in it, and it didn't. So there is no compiler support. I would love to get my hands on it, but I haven't seen it in any of the mainstream releases, and so I eagerly await it. It should make my code a lot faster, because I can use the fast inverse square root, and maybe I can make use of it in other mathematical functions that could benefit from crazy hacks like that were discovered in the dawn of pre-hardware accelerated floating point operations, and have been lost to time. But that story is yet to be told. So let's continue on to a different section. So parallelization. This is probably the most what the fuck kind of thing I did. Everything before it was just working around limitations of ConstExpr, and parallelization is the one that really goes, wait, what? Ray tracing is an embarrassingly parallel algorithm. It is so easy to parallelize that if you weren't trying to, I mean, you should kind of get slapped in the side of the head over it, because it's so easy. Why don't you? When you do a ray trace, each ray is an individual calculation. They have no dependencies between each other. You don't need to do the first pixel and then wait to do the second pixel. Those pixels can be done at the same time, because their outputs are completely independent. I mean, they are not independent if you're doing quantum superposition simulation, but thankfully I'm not doing that, and I do not have the degree in which I could to even begin thinking about how to do that. GPUs are the future, and there's been a whole bunch of hubbubaloo about doing ray tracing in a GPU, and well, that's a whole different talk, but I want to try that out at some point, but not with ConstExpr. That's a different issue. So ConstExpr is not something you can parallelize. It's just not. None of the constructs inside ConstExpr can be parallelized. You can't use thread. You can't use SIMD. You can't use. There's no libraries to do it. So there's just no way, right? Well, not quite. So each ray has to be executed in its own thread of execution. But ConstExpr is a construct that exists inside a translation unit. So when you are compiling your code, each translation unit is a thread of execution. And so I thought, when you're compiling a big project, you generally want a lot of cores, because the compiler can run those translation units in parallel. If I'm somehow able to make the ray tracing work in multiple translation units and then just stitch them together at the end, I can actually parallelize this calculation. And I just kind of went, I'm getting a big brain moment right now, because I think I can do this. There's two challenges with it. The first was stitching the data together, and then the second one I'll describe in a second. So I'm very fortunate that I chose ppm as my output format, because it's brain dead simple and makes the problem of synchronizing different threads output synchronizing is not the right word, aligning different threads output completely seamless, because there's no like width and height, end and start point, start data. It is just a header that says the image type. PPM format is very simple. It has a header that says, hey, I'm a PPM format, which is the P3 you see. It has a width and a height, and then it has a max color value, which is your the bit range of your colors. And then it's just a list of pixels. So the first pixel, and then the new line, and then the second pixel, and then the new line. And each pixel is a triple of RGB integer values. What makes this really easy to use for this purpose is that in some image formats, the difference between row 1 and row 2, there might be some padding or other data in between the rows that I'd have to match up between the different threads, and that would require a lot more processing. But because a PPM is a literal one-dimensional stream of pixels in the form of text, all of that just kind of disappears, and I can just print out the data. It's very easy. So that was a very non-issue in the long run. And so here's some code that there's support for bitcast. Now, does MSVC support dynamic allocation, Jason? Or is that?
I don't know. I didn't dig that far into it. I just thought I would put that update.
That's awesome. But if I don't also have dynamic allocation and virtual functions, I cannot do. I cannot use MSVC quite yet, because the code depends on those features.
Yeah, no,
and I'm not going to re-implement everything.
You would be broken still.
There's hope. Take the water. The example code you have. This is what I tried doing. I had a header file thread dot. Let me use the little mouse pointer. So I have a header file with the function declaration for each bit of execution, and then there's a CPP file where the actual computation happens, and it's a function that returns the ray trace given some parameters. And then I have a main function which includes a bunch of those threads and then simply prints the image, however many threads you have. And I thought I was golden, because I'm like, yeah, I can put each translation unit have its own ConstExpr evaluation, and then I can parallelize this. And then I hit a snafu where the ConstExpr function cannot be forward declared. So the slide doesn't work because I cannot forward declare a ConstExpr function. I have to define it. And if I define the function in the header, that means every file that includes that header also has to do the computation, because translation units are completely separate entities when they're compiled. So you can't. So the main file would also be compiling or executing the ConstExpr function, as well as the thread n.cpp translation unit. So it was like, oh, well, crap. Well, how do I get around this? And this is the thing that I thought would take forever, because I'm like, well, I'm just hitting a limitation of the language. But it turns out I was just being a little bit simple-minded. So ConstExpr functions and ConstExpr variables are translated or compiled or really executed per translation unit, but getting that data doesn't need to be through a ConstExpr function. I was running everything. I was outputting the image at compile time, not at. I was outputting the image at runtime, not compile time. So all I needed was to get the data inside a runtime context, And then that runtime context is actually forwarded, is using the compile time calculated variable. All I'm really trying to say is that if you make a shim function, everything works as you'd expect. So you have a shim function, just like before, but instead of it being ConstExpr, it's just extern. So this is runtime only. Then in your translation unit, you have a local variable that is ConstExpr, and this is where the actual computation happens. But it's because it's inside a CPP file, it's not going to be included by anyone else. Then your runtime function simply returns the compile time calculated constant. And then the main function that gathers everything up is the same as before. And I was like, oh, this actually works surprisingly simply. I thought I would have a big, long road ahead of me to figure out all the little intricacies. And it turns out, because ray tracing is embarrassingly parallel, I don't have to deal with any sort of dependencies of execution. Everything just lives in its own translation unit, and all the object files contain the subsection of the image. One thing I've glossed over is this rat's nest of parameters for the ray trace function. But it's quickly put, you have the full wrong button. You have the full width and height you have to pass in. Then you pass in the width and the height of the section that that thread computes. So in my setup, each thread computes the full width of the output image, but only 1/n of the height. So if I have 4 threads, each thread would compute 1/4 of the height. And then, wrong button again. Come on. There we go. The 0, 1 times height over n is simply the number of pixels. So this is actually just the start point, and the second width and the height divided by n is the starting point, and then the 0 and the 1/height times n is the stopping point. And you can look at the code online and see exactly what I'm doing. And this is just a necessity to break up the work into chunks. That's the only reason I'm explaining it, because otherwise you're like, oh, it's a magic function. It knows exactly what to compute. It's like, no, actually, I have to manually specify what each thread computes separately. And that actually is a little annoying, and I wish I had some build script automation, but oh well. So finally getting to some numbers, an hour and 10 minutes after I started talking. Here is the scene I used. I have 2 materials. Both are diffuse. I have 2 spheres, and no, I have 2 spheres. One is a giant ground sphere, and the other is in the view sphere. And then I have 2 lights. So it's a very simple scene, and this is just for performance comparison. The thing to note is that I do not have any glass or metal metal materials, and that's very, very much on purpose. So the render settings I used, whereas I had a 120 pixel by 120 pixel image output, I did 4 samples per pixel, so I did basically the 4 corners of each pixel, and then I had 3 bounces. So each ray counts at most 3 times into the scene. So if you had a mirror, you could only have you could only see the second bounce in the mirror. That does as many as you could see. I didn't use any fancy benchmarking suite because the order of magnitudes I was using or was seeing did not necessitate anything more accurate. The for ConstExpr, I found the compile time of that simple scene took 22.93 seconds, and then that was all across all the cores. I should have added it. I have a 12-core machine, so I had 12 threads of execution. That's a that's an addendum to add to the slides. Oops. And it took 10 milliseconds to execute. And if you notice that there's 16 millisecond system, yeah, time is not an accurate timing system. Yes, Leslie. I have multiple samples for anti-aliasing purposes. Ben, adjacent pixels are not able to share corner samples. The code I shared at the very beginning was lightly modified so that it fit on the slide. And one of the things I removed was the anti-aliasing code. So you'd have to look at the source code to see exactly what I do to make it not have sharp edges. So I think the execution time is 10 milliseconds according to the time Linux trace utility, and it reports that I have 0 seconds spent in user time. That means all of the time that was spent was doing file system I/O, which I think qualifies me for having the world's fastest ray tracer, because literally the only bottleneck I have is file output. Like, it's so fast, you can't even see it. It literally said 0000. I'm like, well, I guess I have the fastest, you know. Of course, when you have a 22-second compile time, you really can't say in that and not be able to qualify what you mean by fastest. So for comparison, the runtime equivalent took a half a second to compile, and it ran in about 150 milliseconds. Interestingly, I saw exactly the same number of system time. So the file I/O was perfectly consistent across the two runs. But when I was running at runtime, the vast majority of the runtime was spent doing the ray tracing, contrast to compile time, which did 0 seconds. So here's a nice graph. You can see that there is a very big difference between the runtime and the compile time versus the ConstExpr runtime and compile time versus the not so different runtime versions of the running and compilation execution. I think this pretty well shows the problem I'm coming across with. One took 20 seconds to compile, the other took a half second to compile. And I did the math, and that's 146 times slower. But that was the best case I've ever seen. If I had included a lot of glass or metal materials, I was in some rudimentary testing I did a while ago. I was seeing 4,000 times slower code. So like, and I would not be surprised if it got even worse in certain circumstances. So compilation times that are literally 3 to 4 orders of magnitude is not a non-trivial cost. So I think what's interesting is that this ray tracer probably has similar performance metrics to one done in the ray tracers used in the mid-90s. So like Toy Story 1 had probably a similar amount of ray throughput, and it probably was actually faster because it could actually optimize to the machine. But anyways, I just find that interesting how in 25 years we're 4 to 10,000 times faster than we were 25 years ago. It's not just like one generation, it's multiple exponential generations faster. So some thoughts. I'm getting very close to the end, so some thoughts about writing ConstExpr, because I wrote a lot of ConstExpr, as it turns out, to get this working. It feels like Python. I thought it was more similar to Python than C++ in so many respects. It wasn't even funny. Every time I compiled my code, I was also running my code, so I didn't have to compile it and then set up a runtime environment and do all that. It's like, no, you just hit compile and that's it. Compile is run. Um, the Python is probably faster than my Python ray tracer is. I actually have a. If I wrote a Python, I think it'd be faster than the compile time version. Python is not known for being fast, but even Python's not that slow, and you can easily make Python faster with some, Python and other add-ins. So I think a big reason it slows because all of those math functions have to be manually re-implemented. So hopefully C++23 will have ConstExpr math functions, and then everything I just did that makes this talk somewhat interesting can be gone into the wind, and now it's just a moderately slow compile time RayTracer instead of extremely slow. Oh yeah, Leslie mentioned the bytecode interpreter of Python. Yeah, ConstExpr just in compiler when? I would love that. You know. So, sometimes when you're running ConstExpr code, you can't perform an UB. So all of your static analysis tools to catch UB are just kind of pointless. The compiler does it for you. You can't divide by 0. You can't access memory out of bounds. You have to initialize everything. Some of the other minor things is that because it's an interpreter, effectively, it's actually pretty quick to iterate stuff. You just write it out, hit Ninja, and Bob's your uncle. I say that it reduces the bug possibility space drastically, but that's more like causation versus correlation. Because ConstExpr is limited in what you can do, the functions you do end up writing tend to be, they can only do a certain subset of things, so you can't write certain bugs, because you can't do file I.O., for instance. I'm getting, okay.
There was
I can't tell when my audio cut out.
Yeah, it was a bandwidth problem. Your audio got worse, but you should be fine. I believe they were able to hear everything that you said, and I don't know if it was my problem or your problem. Are you still there?
I hear you, Jason, and you were robotic on my end. I am still here.
Okay. Let's just keep going. I think it's pretty good at the moment.
Right. I only have 2 more slides, so.
Okay.
There are some drawbacks to ConstExpr. Debugging is a pain in the butt. It's really hard to figure out exactly what's gone wrong. No, it's actually pretty easy to figure out what's gone wrong if what's gone wrong is divide by 0. Okay, it's divide by 0, but why did you divide by 0? And that's the hard part. You have to pretty much write shim functions that print out the value in the sense that the function takes those parameters in, and because the compiler says, oh, you use this function, I'm going to print out the parameters of that function that you used. And so that was interesting. You also can't use a lot of regular C++, so you can't just do everything you were expecting, but that kind of comes with the territory, so it's less of a drawback and more of just a reality. And while I do have parallel execution, I do not have concurrency in ConstExpr, and I don't think that's ever going to happen. And if it does, it's probably not happening anytime soon, because it's just a different ball game that's just not really necessary at compile time. Everything I'm doing is just to see if it is possible, not to prove it's practical. So, it says better now. Woo! Maybe my roommates were hogging the bandwidth for a minute or 2. Who knows? So, some closing thoughts. So, ConstExpr, the moral of the story is once I wrote those math functions and a few of the utilities, and if I started developing more features for it, for the most part, it would just be like developing normal C++. There's very little that I haven't encountered already that I expect to have difficulty in. The math functions, okay, yeah, math. It's any new math functions I need are going to have to be their own silly implementation. But most everything is dealt with that is hard to deal with. I mean, if I wanted to do crazier things, then I guess I would come up with more walls. But on the whole, because of ConstExpr virtual functions and ConstExpr allocation, a lot of things feel like regular C++, which makes me hesitantly enthusiastic about the ConstExpr reflection proposals, where they're using not templates to do reflection. And that should hopefully be nice and easy to use rather than everything's a template. Oh God, why is the C++ committee so enthusiastic about templates when they seem like such an alienating feature? While that may always be the case, and it's nice not to have reflection gated behind templates, so to speak. Even if templates themselves aren't the most complicated thing in the world, they definitely have that aura. Hot takes aside, ConstExpr is still missing features, but I think 23 will see many of the ones that are most critically missing either added or addressed in some sort of manner. Okay, so thanks for listening. Questions? So now that Ben asks, if you're doing a lot of trig, do you think it'd benefit to use a table-based approach rather than raw calculation each time? I think if you pre-computed a table, yes, you definitely could get a benefit from using a lookup table. The question is, how much time do you want to spend computing that lookup table? Because if you were to hand compute it and like pencil and paper and then type that in, you would not be paying for those calculations every frame, every time you compile. But but if you use the naive approach of actually calculating it at runtime, at compile time, to generate those lookup tables, because you're also using it at compile time, it's a bit of a mixed bag, because the main benefit of compile time computation is you can create a lookup table that you use at runtime. But if I'm also doing it at compile time, there's a cost-benefit analysis, because compile time is runtime in a ConstExpr context. So I haven't invested too heavily into that, but I think it definitely could help. But the real thing is that it would only help until CMath and other math functions get ConstExpr support, and then we can just use the hardware accelerated versions, or at least the compiler's version of those functions maybe is optimized, and not the actual, like, I'm writing ConstExpr code that has to be interpreted to calculate those things. The compiler could write a sine, cosine, and tangent that, while it may not use actual silicon hardware acceleration, it could at least use compiled C++ ahead of time and not ConstExpr interpreted code. So
there's two earlier questions that we can get back to. Leslie was asking about that const eval on slide 31. I'm kind of curious about that myself, if you want to string back to that and see if anyone else posts questions in the chat in the meantime.
Go to slide 31.
31 or 30.
So, yes, it was 31.
So populate data, he said, can only be called at compile time. So should it therefore be const eval?
Oh, I did not understand that part of it. Yes, it should be const eval in this context.
Okay.
Because it's a compiler error if you try to do it without it. Wait, no, it isn't. Wait, no, it is. Okay. I was thinking if you just where's my mouse? If you just slapped off the ConstExpr, this is a very valid function. But then I remember that the ConstExpr keyword means it has to be used. It has to be a viable ConstExpr function. And since you cannot return dynamic memory outside of ConstExpr, and outside to a non-ConstExpr context, yeah, you need const-eval.
Oh, so you're saying get ConstExpr array should be const-eval because you're not allowed to let that escape. That's a good point. He was asking about
Yeah.
populate data, which I believe could be called in either context. It's just the problem is you just have to know the size at compile time.
Yeah.
Oh.
You can't have it as const eval because, well,
No. If get ConstExpr it should be const-eval, then populate data should also be const-eval because it's one calling the other.
right. And then get size as const eval as well. Okay, no, because everything is compile time, everything should be const eval.
Interesting.
And it's just because a few people decided a few people decided is a mischaracterization. What I mean to say is that the C++ committee decided that the paper to get dynamic allocations to live on to ConstExpr dynamic allocations to live on to runtime was not implementable at the moment, and
Right.
so they axed it from C++ 20. So we get to live with this lovely slide of boilerplate and other things if you want to do purely compile time computation that has a non-static size.
All right, so the other question...
Until hopefully at least 23. Oh, no, I'm fine.
The other question then was whether or not you have ConstExpr tests. Are you testing your code at all, really?
Yes. Now that I'm through the slides, let me pull that up. Test util. So if this is, it's going to be a delay, so I'll try to do it. So I have a couple of static asserts.
Yeah, that might be a little small.
My
okay.
nearly, yeah. Okay. Is that better?
It's fine on my
Probably
side,
delay.
but I'm cheating.
Well, yes. Yeah. I have a nearly equal function, which is a floating point comparison that is ConstExpr. I didn't get into it because floating point comparison is a super complex subject, and I didn't want to bog down an already kind of bogged down talk because I did a lot of discussion explanation of what ray tracing is, because I felt the context was necessary, so that people understand what I'm doing, not just that it is ConstExpr and the problems I covered. I have the stream up in another monitor, and I don't see my tests up yet.
I agree. That also seems to be taking a while to come up.
Oh, I was not at the live broadcast. That was weird. Anyways, okay. And
Yeah, I see
just
it, guys.
put in a
Live broadcast.
Okay.
Okay, good. I have a bunch of functions, and they hopefully illustrate a little bit of the floating point weirdness, where the 0.0 is equal to a lot of zeros followed by a 1, whereas 0.1 is not nearly as accurate. Okay, yeah, okay, the code is a good size. I'm getting comment. So I have those nearly equals, and then I have square root functions where I tested square root comparison. Yeah. So, and then I have a couple of power functions. I should have more tests, but this was more for sanity checking. Do these functions work at all? Because I was getting some very weird artifacts. So most of the tests are more reactionary than proactionary.
Would it be reasonable for there to have been a ConstExpr test that says ray trace this scene and these 4 pixels should be exactly this color?
Yes, you definitely can do that. I think ground, that kind of testing is very applicable in this situation in ray tracing, because you can know everything about the simulation that's going on, and if you don't get perfect results, the problem with that is that you have to know what those 4 pixels should be ahead of time.
Right.
And I'm really lazy and didn't want to have to do all that math by hand, or using some other possibly not as accurate method, or not as accurate is not the right word, not as reliable. Like, I could have used a different RayTracer, but because they have different implementations of the functions, they could have slightly different results, and the exact numerical value might have been slightly different. The truth is that there are far more interesting things to do before that becomes a necessity. Because it's all visual output. So if the visual output looks wrong, the visual output is wrong. There's a lot of things that go between that tested, and that just look at the visual output tests are not as helpful when you don't have nearly as much code as a production full scale 20 years and 20 engineering years effort work into it.
Right.
This is just a hacking project. There's another tests file, and this is for the various I think there'll be some delay, but this is various vector functions. So making sure that vec0 and vec1 are what they say they are, and squared length is important. Why do I have 25? Oh, right, because they're 4 different parameters. I was like, why do I have the same test 3 times? I was like, no, it's because there's 3 different inputs. Making sure that the X, Y, and the Z are, you can switch any of them and they'll be all the same output. I didn't have any tests here. Okay. Well, that's the extent of my testing.
I would like to comment here. Leslie says Catch2 has static require, which if you haven't seen that, you can use Catch as static require utility also.
Oh, so there is ConstExpr support is what I'm hearing, right?
Yes, and perhaps maybe more importantly is with a preprocessor define, you can switch it between compile time and runtime mode, which then could help you debug these tests when they fail.
That's pretty handy.
Nice.
Or you just have it like me, where if you run the test at runtime, you run the tests, and if you compile the test, you run it at compile time. So, I just remembered that I did that. The code here is, it always exercises the test when you compile it.
Right.
Which is fun. Because it's a compile time constant. Anyways, actually, so yeah, okay, so I can use Catch2. That's one of the reasons I didn't, immediately reach for a known testing library framework, was I didn't know if there was ConstExpr support, and I didn't really want to bother to check, because I'm like, do I want to set up a library only to find out it doesn't work the way I need it, or do I just write a couple of functions with the ConstExpr name in front of it and call it a day? And it was also Christmas break at the time, or holiday break, whatever, and so that's the route I chose. Anyone have any requests for code to look at in person rather than on your own in your free time, or do we want to wrap this up?
I have one question on my own, personally. I was curious if you looked at the binary size difference between the runtime and compile time versions. Like, how big did the binary blow up if it had all that data in it?
So, cert is the... Let me... and where is RT runtime? So, apparently there's only a 10 kilobyte difference.
Interesting.
If I'm reading the data correctly. And then if we look at the output.ppm compile time, you notice that the output is so this is the output image, and it is 3 times the size of the binary, because the binary stores it probably it stores it as integers,
Right.
whereas the text stores it as ASCII text. So it's actually more efficient to binary. I could implement a like a stb image.h, and that has like JSON, PEG, and PG out. But I didn't really see the need. Got the PPM format working because it's like, well, I can get the image just fine. So all I'm saving is a couple of kilobytes here and there.
Right.
Compile time test or the next ring of hell, pass W error. Oh.
So Charles, this has been great. I think Jason, maybe we should declare April, the month of April, as ray tracing month for the C++ meetup, since we've now done 2 different ones. One 3 years ago, though. So, but no, I loved your talk, Charles. Great job on
Thank
this.
you. If you want this to be ray tracing month, definitely check out Ray Tracing in a Weekend as a place to get started. It really is, you can do it in a weekend, and then you will have a ray tracer. And in fact, you may have a ray tracer that's better than mine, because then you won't be dealing. You don't have to, but ConstExpr throws a lot of roadblocks in the way. It took me more than 1 weekend to get to the end of ray tracing in 1 weekend. Let's just put it that way. You can definitely bother me. I don't know if you. I don't have a link to like my email, but it's my email is cdgeeson@gmail.com, the same as my GitHub account. What is it? So I just add it here. Why am I bothering? Okay, cdgeeson@gmail.com. Just make this big.
Do you care that that'll be on the internet forever?
Well, it's already on the internet, so I mean.
All right. Something happened when you can
I don't
no
think
longer
I've.
It's like you saved the file.
No, I deleted it for some reason. I didn't mean to. There.
Okay.
I'm also going to call out Leslie and Ben as other people you can bother about ray tracing, because I know they have done it before. So, if you feel called out, well, oh well. But I don't know their emails, and so I'm not going to try to put them up and, for all the world to remember forever and ever.
They're both on Twitter. Someone can find them eventually.
Yes. Yes, and they both have GitHubs, I believe.
Yes.
So, anyways, well, it was a pleasure coming up with all the slides to talk about, and then actually talking about it instead of just theoretical thinking about, well, what if I gave a presentation about this silly project I did over Christmas?
Okay, so
That's great.
Yeah, thanks.
Okay.
I guess we'll be doing the virtual pub thing here in a few minutes. I'm gonna need a couple minutes myself to get organized for that. So in about 15 or 20 minutes, for those of you who are planning to attend that, we can jump over to there. If you've already RSVP'd on the Meetup page, then you know the link to that. Any other comments, Scott?
No, I don't think so. Again, just thanks, Charles. Thanks for everybody for joining us. Thanks for taking time out. Hope everybody's figuring out the work from home world that we all live in right now and are staying safe. So thanks again for everybody attending. We'll be putting something out for May. In June, I know we're looking to have Chris and Dave do a presentation on unit testing in C++ and some theoretical, some with the micro T testing framework that Chris has developed. And so more on that to come.
Excellent. All right, I'll shut
Thanks,
this
Jason.
down.
Thanks, Charles. All right.
See y'all in a bit.
See you, everybody.
Bye.